Hello and welcome to this wonderful presentation with Dr. Shaista Hussain. Dr. Shaista is the co founder of SafeCheck, and she is actually a clinical pathologist that turned into an AI and ML expert. She's focused on championing responsible and explainable AI to support the regulatory compliance environment. So, if, would you like to just give a 30-second thing on Safe and the sword and how
I
you're a
will.
protector?
I'll start first quickly by saying, Joaquin, thank you. Your productions are the best in town, the best around, the best in the world. I'm always grateful to participate with you. I'm always grateful when I see the other participants who or other speakers that you've acquired for these sort of conferences. And I believe as much as we're all getting to the spotlight and recognition for sharing important topics, I think you should get a lot of credit and kudos. So well done to you, Joaquin, and the Swarm community. I'll quickly introduce SafeCheck. As it says, is to know trustworthy AI. We have a safe, which in Arabic is a sword, which is kind of the sword that you see here in the logo. But there's also a check mark in the logo. So the idea is we've got the shield of protection and we've got the sword for protection. And essentially our ethos is to to nurture an AI ecosystem or environment that respects and develops responsibly, trustworthy, and explainable artificial intelligence in such a way that it protects the customer and the end user. So that said, I'll give it a go. I'll get started.
All right.
Thank you. Um, SafeCheck itself, just to give you an additional in depth of what we do, is we provide risk assessments for existing AI models, and then we offer you on those risk assessments analytic reports that tell you what's going right and what's not going right. And whatever's not going right, we suggest for you ways in which you can optimize or fix the non-optimal aspects of your AI. And then for passing scores, so we give you a score on how well you did, an A plus, a B minus, a C plus, whatever. And then for passing scores, you can expect a digital certificate, which is very much just this badge with your model information and the model version. And then that is something that you can put on your products to tell customers we've been evaluated by a third party for our safety and security. The aspects that we look at are we have multiple regional regulatory compliances. We look at performance metrics in the model evaluation. We look at data quality and data safety and security. We can examine large language models, generative models, and then we have end user safety, things like child safety and disability safety for your different models. So I'll start with what's XAI, explainable AI. We'll say XAI, that's the sort of accepted abbreviation, which is for explainable AI. Explainable AI, it's essentially the way in which a human can understand what the machine did. So similar to our last speaker who said large language models specifically just retrieve language, we need to know that as end users instead of believing that there's a genie behind the laptop screen or your phone screen. And we want to know, how does it make these decisions? When you use XAI and you learn how to make these decisions, you empower your customer or your end user with accuracy for your model, fairness in terms of understanding how confident a model is in making its decision, and transparency for your own business operations. So this is my famous example I always give. But for example, if you had an AI app, so to speak, or an AI system or solution, and you were allowed to upload a photo and say, identify this image or this object, and it says, well, this is an insect. Sure. Okay. How do you know it's an insect? And so there's a small image here of a SHAP graph, which we'll get into, which tells you the different reasons that the model is confident and how confident it is for each of the selected variables. And then you know that it's an insect. As an end user, you can then look at it and say, actually, the AI system is correct, or the AI system made a faulty judgment. So that's what XAI is. It's a set of processes to differentiate what's in a black box where you don't see what's happening in the background of the model, and then a white box or a transparent box where you can see what's happening. You can see the sort of impact of different nodes within the neural network and how that leads to a prediction or an output. So when we say explainable AI, we want to know, what are we explaining? You're explaining, yes, number one, what's happening inside the black box. What's inside the black box is a combination of the data that's been trained in the model, the method of prediction, so the neural network itself, and the algorithms itself. So what that means is, if you've trained a computer vision model, like that insect one that we just saw, if you've trained it on multiple insects from within your region, uh, when your model is deployed and somebody uses it in an area on the other end of planet Earth, your model may not detect what insect they have. So when you do explainable AI, essentially what you're doing is you're explaining within the output that these are the items, these were the insects that the model was trained on. The predictions are like what we saw in the example. It has these particular features. It has wings. It has 6 legs. It has lateral eyes. And so now you're explaining how confident the prediction is. So you say, because it has wings, we are 99, the model is 99% sure. Because it has 6 legs, 99% sure. Because it's blue and yellow, it could be a bird, it could be something else, so less confidence. And then lastly, you explain the sort of thresholds for the prediction within the different layers. So there are different networks that have 16 layers, 19 layers, etc. And then you explain how many decision-making steps that the model went through to get to its final output. So that you're explaining the data, the predictions, and the algorithms itself. And this is part of that transparency that we said is the benefit of XAI. And what do you get from it? Why do you do it? So on the side here, you can see currently how machine learning models are used in practice, where somebody will ask a question, what is this picture? It's an insect. Why is it not a bird? Why are you sure it's an insect? What happens if it's not really an insect and you misdiagnosed or you misconfirmed or you have a wrong output? When you have explainable AI and you have this interface that shows these confidence, you understand why not, what happens if it's correct, what happens if it's not correct. And so for executors or business owners, this helps with informed decision making. And I'll give you a couple of use cases in a minute. But in terms of informed decision making, what we're talking about is you don't have to presume that, oh, we have an LLM that speaks to our customers and it's always going to be right. You understand where its vulnerabilities are, you understand where its strengths are. And you can assess, then you can do an evaluation as to whether what you have intended as a business goal is being matched by the output of the AI. This will lead to a reduction in your risks, because if your LLM, for example, hallucinates when it's speaking to a customer and gives the customer wrong information simply from poor training or poor retrieval networks, well, then you've got a risk to your reputation and even litigation risks. When you give that confidence score, so for example, if you went to any GPT model that's out there in the open AI, for example, or Gemini, whatever's out there, and it says, you ask it a question, what's 2 plus 2? And it says 2 plus 2 equals 4. And if it's got a citation at the end, that gives end users confidence that it came from somewhere reliable. If you give it a citation plus a mathematical explanation or a calculator output, end user has more confidence. The other thing explainability does that is crucial for all businesses from, I'd say, the beginning of this year moving on, and it's only going to get more extreme and strict, is governance. And that's meeting local regulations and governance laws, where you have to comply by certain transparency metrics in order to keep your AI business alive. And lastly, it's for efficiency, so that if you have a model in production for your business and you don't know what's going on, you can't say how well it's doing or how poorly it's doing the way you would with any human staff within your organization. So if you have great employees, one person who's in sales is making $150 million in sales a year, you have that output, that metric to be able to say, I know this guy is selling really well, or I know this girl is doing her engineering work very well because these are her outputs. We don't have that with AI in production commercially at the moment. And when you have explainable AI embedded in your process, you now have those metrics to evaluate how well it's doing. So I mentioned I'll give you some use cases. Here are some. One of the things you can do is with your AI analytics models, you can look at things like customer churn rate, how well your customers are doing in use of the app, how quickly they turn over from visitors into customers. And you have all this data that you're collecting in terms of website visits and traffic or app usage and downtime. And you can make sort of informed business decisions like that. We talked about risk reduction. And so if we're looking at risk reduction, you can use graphs like permutation and CHAP, ROC, which we'll cover shortly. But if you have this kind of data and you can select what kind of models you want to use, if it's regression or XGBoost, you can then say which of the following AI algorithms are the most optimal for us to achieve what our business goals are. And then that takes us to the other side. So from the end user side, you want to understand what's going on with the model. From a customer point of view, we'll say it's a customer who's downloaded an AI system or a solution on their phone or on their laptop. From their perspective, they're looking at the output, that confidence score and those graphs, and they have something called interpretability. And it's their ability to determine the cause and effect for a decision that was made. Similarly, if you were talking to another human and you wanted to know, why did that person just smile at me? Oh, it's because I'm wearing a Batman t-shirt and they like Batman. Or they got angry. Why did they get angry? Because I'm wearing blue and red, which are the colors of some football team that they don't like, for example. So that ability to determine cause and effect from the end user's point of view is called interpretability. From the engineering point of view, you have explainability models, which give you these graph nodes and confidence scores, and they're two sides of the same coin. It's what you see and then how you interpret it. And a quick example here, just as Joaquin mentioned, I'm a pathologist. So you look here, and this is a pathology slide where traditionally pathologists look at this under the microscope and they're tasked with determining whether there's cancer or not cancer, and if there is, at what stage it's at. When using computer vision, and there's some extraordinary products out in the market at the moment, something like a Lyme, which Lyme is one of the methods we'll talk about for XAI. Lyme highlights the areas that are deemed cancerous, and that is based on what you've trained the model to detect as being healthy tissue or unhealthy tissue. So for the end user who wants to understand the cause and effect, or wants to understand what's going on here, with an explainability model like Lyme, you can outline exactly where the problem area is. And if you were a physician, you could then tell your patient, yo, check it. This is cancer because look here, look here, look here. Whereas traditionally in pathology, we would just say, I've got 20 or 50 years experience looking at these slides, and I can tell you that this is or is not cancer. So I'll give you now some examples of the commonest models. These are names. If you're in the XAI game, so these are not all by any means. There's a lot more, but these are sort of the commonest models that you'll run across, and we'll explain these now shortly. And let me go into them. Those same models that I just listed here are in this graph just to show you that there's a very finite and definite system of selecting which explainability models to use for which type of data and for which type of prediction output. Meaning, in artificial intelligence, you largely have predictor models that are predicting something, like in large language models, you're predicting which words match this response, or predictive text, what words come next. Or you can have classification models where you're looking at an image or a video data set and you're saying, what is this, or what is this thing doing? And that's the first sort of major branch. But when we talk about explainability, we want to talk about, does the model already show what it's doing, or does it not show? Is it black box or white box? And then the next step we look at is something is its agnosticism, whether something requires explanations or doesn't require explanations, whether it's specific to just a predictor or not. So some explainable algorithms can be used for predictors and classifiers. Some can be used just for prediction. And so this is just to justify that there is a system to be used. Before we go into some examples, two definitions that are worthy of absorbing at this stage. When we talk about a global explanation, we're talking about the most important features in the model and how they influence the prediction. For reference, if you had a heart attack predictor model and somebody were to enter their symptoms into some sort of symptom checker, and then they say, what is this? The model would say, this is most likely the beginning of a heart attack, or something else, or it's muscular, or whatever the other differential diagnosis might be. How do you know that it's a heart attack? Because the person had chest pain, the person had shortness of breath, their age, their gender, etc. So those specific features give confidence. We call that a global explanation. On the other hand, you have local explanations, which As an example, if you were looking for somebody's credit risk rating, they would look at specific factors only within a larger database of information and say, to predict this specific item, we only need to look at the spending history or the income, and those are the specific features. So, examples. The first one, like we saw in that butterfly thing, and like that heart attack example I gave, is SHAP, Shapley Additive Explanations, and for short we say SHAP. SHAP is one of the funnest, most fun explainable models that can be used. It was actually developed originally for a game theoretic approach, meaning it used ensembles, and the change of an outcome can be explained. What that means is the different features are highlighted from the training data, and the SHAP value, which is the curve here, the lines here, will tell you the impact of any specific feature on the model's final prediction. And then the color just sort of says how high or how low the feature value was. So, for example, if this was the heart attack example, for example, you could say gender. So if it was a male or a female, males tend to have at a certain age a higher risk of heart attacks than females do. So that gender and that age might be more pink and have a longer line or a higher value. If the next person who uses the model has different demographic data, then that would change. Those features would be, the attributes would change and the output would change. What this does, though, is for a company owner or an engineer or the end user, is they can see how much that a certain feature impacted the model's decision to say this is a heart attack or it's not a heart attack. Lyme, which we talked about in that cancer example, does something very cool, and it's local. So where SHAP was global and local, Lyme is local, where we said we look for specific features. And in the cancer example, the slides, the histopathology slides, you would have trained the model to say when the borders are irregular or when the cell is slightly darker at the edges, this is considered a sign of cancer. Highlight it if you find it. So what the Lyme model does is it takes the original picture, it'll pre-process the image and look for those features that it's been trained to look for. When it finds it, it highlights it on the original image. And so we say that this is a method to predict the local neighborhood, what's happening around certain data points. And that's in images. Lyme can also be used for tabular data, so stuff you'd find in an Excel sheet. And then it sort of gives you, again, the features that were trained and the value of importance it has. And it gives you something like this, an output, a predicted value with a score of its confidence. PDPs, or partial dependence plot, is another example that can be used. This, on the other, unlike Lyme, this is global, where we said it takes in all sorts of features at once. And this is a very famous data set that's been used, I guess, by most people who are in data science or engineering. And it's the California housing data set. It used gradient boosting. But you'll see here that this sort of topographical looking map here will show you the effect of one or more features on the outcome. So this is great when you have multiple features at once that can create an output. For example, if you're using computer vision and you're saying, is this a car or a bus or a bicycle? And then you have certain features associated with each, that a car is usually mid-size, a bus is very large, they all have 4 wheels, they all have 6 windows, whatever it might be. You can see the impact of each subsequent combination of features on the model's final decision. And it assumes that the one problem with this is it assumes that the features are independent. So it doesn't say 4 wheels plus 6 windows equals a bus. It says 4 wheels and it puts it in a vehicle category. And then it says 6 windows, some type, it's not a bicycle. And then it sort of does it in iterations. So there's good and bad with this particular XAI model. Another one is more sensitivity. This graph makes it look very complicated. And I guess mathematically, you could argue it is complicated. The output you get with a more sensitivity is very similar to that Lyme graph output, where you get 2 features and a confidence score. And this is something called one step at a time, or OAT, global sensitivity analysis, where it's used for screening, where inputs are very important for further analysis. For example, in a pathology example, if you were looking at a whole slide image, more sensitivity is great for the pathologist, not necessarily for the patient, but for the pathologist to be able to say, if the cell borders didn't look right and the color of the cell didn't look right and the nucleus didn't look right, And so you've got these inputs which are all important. Should that cell border now be evaluated even further for maybe it's not a cancer, maybe it's an infection? So more sensitivity gives you very specific two-feature analysis, a lot like a heat map where you have the strength of the relationship between two features at a given time. CEM, or contrastive explanation method, yet another example, and it's a very commonly seen one. And so this one is local, and it generates an instance-based local black box explanation. So it tells you these particular features are definitely positive. These particular features are definitely negative, meaning it is definitely a heart attack or it is definitely not a heart attack. And that's really good to be very sure about which direction a model is taking in its decision-making ability. We have Proto-Dash, which is something that was quite popular a while back, and I guess now it's still used, but more at the engineering back end. And so when you have handwriting script that you want a computer vision model to read, so for example, when you have PDFs and you wanted to translate that into a Google Doc or into a Word doc, and it has to determine what's written there. If it was written and then a photo was taken and this document was turned into a PDF, you might want to find prototypes for that model. So your training model would have had to had all sorts of different ways that you write the number 3 or the number 0, the number 8. And as a common example, you see most people write the number 5 very uniquely. There aren't usually two people that have the same way of doing the number 5. A proto-dash would be great because you have prototypes for many different versions of how number 5 looks so that it doesn't confuse a number 5 with the letter S, for example. Tree surrogates are used in so many of the more high-end models now, and yet the concept is still remains simple. What's great about tree surrogates, and why you'll see it being used in a lot of places, is it's both global and it's local, and it gives you specific numbers associated with each step of the prediction. Meaning, I told you before that models take a stepwise decision-making process before it gives you an output. At each step of that process, you'll get a confidence score, so to speak, that aligns with what happens in this flow chart. So for example, if we go with the symptoms and somebody had chest pain, you would say, is it a male or a female? And that would be the first branch. Okay, it's male. Now the confidence score for a heart attack might be higher than it would be for the female. Next step, what's the age of the individual? So the age is under the age of 40 or over the age of 40. If they say under, now that confidence for chest pain leads the model towards a different diagnosis. If you say over the age of 40, you know that risk is higher versus the female who is, usually females tend not to get heart attacks until after menopause. So you'd say under the age of 50 or over the age of 50 for a similar process. So these kind of decision model trees are essentially what our brain does at a very concrete level in terms of trying to decide how to make a diagnosis or how to make a decision. I go to the shop, I want something cold. Do I want a drink or do I want ice cream? You make a certain decision in your mind as to, no, I'm very thirsty. Thirsty, go with a beverage. Go to the beverage, to the fridge. Which drink do you want? Do you want something very sugary or do you want something healthy? And so the same way you make that decision process is the way tree surrogates work. In the case of machine learning, you also get this sort of confidence score at each step along the way. Scalable Bayesian rule lists. Whenever you see Bayesian, you're pretty much looking at probabilities. And the great thing about probabilities is probability means how likely something is to happen. So these Bayesian rule lists are global and local, and they learn from the data. And when I say learn, I mean for each subsequent response that it gives out, the decision ruling system, much like the tree decision, becomes more advanced because you have an if-then. So if the shop has drinks or if the shop has ice cream, I will make that decision. So if they have drinks, I'm going to go for a beverage. If they have beverages, I want something cold, not hot. If they have something cold, I prefer something in a can rather than a bottle. And so you have this if-then, if this, then that, and with probability scores for each subsequent decision that's made based on availability. Huge fan of anything Bayesian. EBM is a Microsoft concoction creation, both global and local. Interpreting the output is very nice and smooth and easy. It uses something called bagging, which is something like a filtration process, which means it's a little bit slow to train, but it makes predictions very quickly. The last is something I won't spend time on because our last speaker spent a lot of time on it, but knowledge graphs, which have quickly come on the scene as the new actor on stage, or it's taken main stage, so to speak. And this is sort of reasoning mechanisms. And essentially, knowledge graphs are not that complicated. They are graphs that show the relationship between different things. If you had a huge database filled with something like what we have in SafeCheck, we have a database filled with thousands of documents, for example. You'd want to categorize those documents. Are they regulatory compliance documents? Are they algorithmic documents? Are they end user safety documents? And then they have a connection because they're all related to responsible AI. That graph can then go deeper within the regulatory compliance. You can say, is it at a national level, or is it at a local level? Is it at a regional level? And then again, you draw these relationship lines between the various points, connecting how a system stores and retrieves specific information. So it's inference and causation. You have a few use cases. This is by no means a very comprehensive list of examples, but for the average listener, the average viewer, in finance, why would you want explainable AI? If you're making decisions about a customer and there's somebody behind the desk, like a bank teller, who's able to assess, does this character look like they're about to rob the bank, or does this character look like they are actually interested in taking out a loan? Next step, let them fill out a form. Based on the responses of that form, you'll say this character deserves a loan or doesn't deserve a loan. And when we allow artificial intelligence to take over these kinds of jobs, you want to make sure that each step of each decision along the way has been made confidently and with the right reasoning, so as not to cause any discriminatory outputs. And it's happened. We've seen some of the HR apps that are out there that are AI based have showed discrimination against either men or women or people of certain socioeconomic demographics or political affiliations. And that only further enhances issues we already have as humans, but you don't want that leaking down into the AI system. So in finance, you definitely want to be sure of each decision step along the way. Auto vehicles, so these sort of EV cars on the road who are driving without, that are driverless, they have to make rapid decisions very quickly, so that if the computer screen for the CV model that's operating the vehicle says this is a tree and it's been trained not to drive into a tree, you'd want to be sure that it recognizes that that's a tree and not a human, or that's a speed bump and not, for example, a dog crossing the road. And you'd want to make sure that those quick decisions that are being made have some visual output for confidence and for correct feature analysis and data training. Last thing, we've talked a lot about it, overkill on the diagnostics, but definitely in healthcare, it's a huge industry that people rely on the outcomes that their doctors are saying. And if the doctors become, it can happen, we know some doctors who can be lazy in terms of their explanations to their patients. And then if they're using an AI and they say, well, the AI said it, that's not going to cut it for the average patient. So just a quick example, we're almost done. Here's an example of another diagnostic slide. And when you see the XA, so this HistoMapper is a company that came out several years ago. Huge salute to them for being way ahead of the game. And what they've done is great here is they list the features that say why they've come up with a certain diagnosis with a confidence score. And they also let their end users agree or disagree or finalize, so that their model can be human-centered, data-centric, and controlled by the person who's interpreting it at the end. Another quick example here, you've got an X-ray and you want to say, what is this? Diagnose this for me. Where a human would have to look very closely and look at breaks in the bone lines, and if your eye was blurry or you had something in your eye or you were sleepy, you might not pick stuff up. So diagnostic with explainable AI works then. So just last slide on best practices. Explainable AI is important for governance, whether you're a business owner or you're in the government. You need to make sure that when you're using it, you have the right talent, that you use it throughout the AI lifecycle, that you consider your end users, if they're children or if they're adults, what kind of interpretability do you want them to have, selecting the AI, whether you want it global or local, how often you evaluate and test your AI for bias or for changes, and that you're constantly monitoring and updating your explainable algorithms. So these are sort of the best practices, and I'd be happy to share this slide later if anyone wanted to go through it in more detail. Reach out to us at safecheck.ai. And again, a huge thank you to Joaquin for allowing the world a chance to hear the truths from all of us.
It's an incredible pleasure to learn from you. It's always a great opportunity to, you know, get a reminder as to why we're engaging in this kind of work, producing these events, or just communicating these ideas. Artificial intelligence is a very powerful technology that has a disproportionate impact in society. I mean, the whole idea of organizations wanting to install AI is because they think it'll help them derive some sort of value or reduce costs with work. And what they don't stand still to acknowledge is whatever that touches, whatever people that it impacts, if it's not right, it's going to impact them negatively. So
Everything comes at a cost. Nothing comes for free. So you're not going to save costs in your business unless you make the effort or hire the right people now to evaluate. It's like quality assurance. If you're in an assembly line, you can say, we've got the assembly line, we're producing the product faster. Are you producing it well at each stage, or is there a cog loose along the way?
yeah,
So, anyway, thank you.
thank you. All right, well, we're gonna close this one out, and just join us in for the next one. It'll be 9 minutes away. Ciao.
Ciao.